Okay, on to theorem 23 in section 8.9. This deals with remainder estimation. And we're back here to our equation. Here's our Taylor polynomial ending after the nth derivative. And now here we have our estimation of the remainder. This is R. In general, of course, we don't know what C is. And so we're asking the question, well, how bad can it be? How big can this remainder be? Well, you know, before we had an example where we said, well, if we were looking at estimate e to the x, this nth plus 1 derivative would simply be e to the c. And if we had an example where it was a Maclaurin series, we were centered at 0, and here is our x above 0, we would know c was somewhere in here, and we could say that an upward bracket would be e to the x, okay? And so we might say that if we substitute in e to the x in here, then our error term could be no worse than that. In that case, we would be using this idea of a substitution. So let's make this a little more formal, as they do in theorem 23, and say the absolute value of Rn of x is going to be less than or equal to m, which is our fudge factor. Nothing more than a fudge factor. It's going to be right here. It's sitting right here. It's the n plus 1 derivative evaluated at c, but of course we don't know what this is, so we fudge a factor in there and call it m, times, and then it's just the rest of this term, absolute value of x minus a raised to the n plus 1 value power over n plus 1 factorial. Okay, now you might want to, in this case, say, well, we could substitute in e to the x, but of course we're trying to estimate e to the x. We don't actually know what e to the x is. Maybe, I don't know, I'm just making this up. Maybe we should say we know that e is less than 3, and if we know that's true, why don't we simply substitute in 3 to the x? We'll assume we can calculate that, and perhaps we could substitute that in. You can go and work through some of these examples in the book. It might be useful to look at them quickly, where they use cosine of x. They're trying to estimate that, or sine x. It wouldn't really matter. And in these cases, they say, well, what are we going to use for m? How big can this be? Well, derivatives of cosine and sine are just going to be sequentially, you know, sines and cosines on forever. And they never take an absolute value greater than 1, right? So if we substitute in 1 here, that will be the worst case scenario. The absolute value here, just 1, will be the worst case scenario for the absolute values of this. Now, it could be much smaller, but that's really not the point here. The point is we want an upward bound on how bad it can be. And then this term here, which, by the way, as n goes to infinity is going to 0, is what's going to be used to see how small is our error term. So m is a fudge factor, and then we allow this term here to kind of grind it down. And you might work through examples, let's see here, 2 and 3, and see exactly how that works.